Okay, so here's what we were talking about last time. We were talking about inner product spaces. And remember, the idea of an inner product space is it's all sort of modeled on Rn. Kind of like vector spaces were. I mean, our big idea of a vector space was, look, certain situations that we find ourselves interested in, everything that's involved, I mean, you can add them, you can scalar multiply. They behave just like vectors in Rn in the sense of addition and scalar vector multiplication. So all we're doing here is saying we're looking for little worlds, little stories where things behave like Rn, just like with vector spaces, in the sense of addition, in the sense of scalar multiplication, but then also furthermore in the sense of kind of like the dot product used to work. Thus, these properties that we want our new additional, our third operation, our inner product, we call it, to satisfy those four additional properties. So it's like a vector space, but more so, right? An additional operation that behaves in certain ways, but all still a rip-off, just a more sophisticated rip-off of Rn. Okay, so we talked about some examples last time. Let's see, here we go. So, no surprise, Rn being the model for this new construction, no surprise, it satisfies the requirements of this construction. Well, it better. Okay. Here's here's the kind of the weird one. Take this vector space and think back to chapter 2, collection of all continuous functions on this closed interval from A to B. That's a vector space. Not hard to show. You can add, you can multiply by scalars. Let's now throw in this new additional operation called the L2 inner product. Now we have not just a vector space, now we have an inner product space. Okay. All right. And there's another example here. We talked about that one last time. Let's go back to this list of conditions. Quick reminder, we use these four properties of the dot product as our model for the definition of an inner product space. So I'm going to say definition here. Don't forget that these we don't have to make part of the definition because these come along for free. Right? Anything that satisfies what I'm going to call those first four properties must immediately, as a consequence, also for free, every time, no question, satisfy these blue circled properties. Okay. And then where we ended last time was consideration of, well, what are we going to do about these properties? Well, we can't decide whether they're true or not true because we don't have an existing notion in our new concept of an inner product space of what is a magnitude and what is an angle. Right? Everything that I have circled there. These there are no pre-existing ideas of angle. What the angle between two matrices was the sort of preposterous question that I proposed last time. Right? So, because those notions don't previously exist, we can use these to make definitions. And so we're going to use this formula here then as kind of the definition of a notion of magnitude. Anytime you have a new inner product, then analogous to how we use the dot product here, we construct from that new inner product, we construct a new notion of magnitude, sometimes called a norm. And likewise, from this, we get a definition of angle. Don't have a notion of angle in your little world? Well, if you have an inner product, that inner product, analogous to how we use the dot product here, you can use the analogous formula to come up with a notion of angle, weird though it may seem to do so, a notion of angle in your new inner product space. So here's an example of that. So let's find the angle between these two vectors sitting inside that inner product space. And again, I want to start this example by observing what a preposterous question this is. Right? This is an abstract, infinite dimensional inner product space. Right? This is not R3. Right? But because it has certain operations that behave just like certain operations in R3 that we can associate to angles, we can make a definition of angle here. Right? So even though I can't, these don't have like Euclidean like directions that they're pointing. I can't draw a picture of the angle that I'm being asked to compute here, but I can still compute it by the analogous formulas. So here we go. Here's our definition of angle. Notice we're going to have to do some computations. On the one hand, I'm going to have to compute the inner product of these two vectors in this inner product space. Okay, well, that's going to be a calculation. I'm also going to have to compute the norm of that first vector. That's going to be another calculation, and then likewise, I'm going to have to compute the norm of that other vector. Those calculations proceed straight out of this formula. That's how you compute a norm. The square root of the self-inner product of that vector. All right, plug and chug time. I'm going to mostly leave this as for y'all to go through and compute on your own. You may recall that Math 212 is prerequisite to this course, and let's say Calc 2 is prerequisite to Math 212. So I hope y'all still remember how to do all your Calc 2 integrals. They don't come up a tremendous amount in this course, but they do come up a little bit, and this is one of the places. There will be several other places, by the way, where Calc 2, antiderivatives, etc. is just it's going to be around. So from the formula on the previous page, that's how you compute a norm, a magnitude. Right? This integral here is pi, as it turns out. Thus, that norm is the square root of pi. Now, make sure you can do that integral. That's I'm going to leave to you, right? You may have vague memories of how to do these kinds of integrals. You may even remember that there is a trick in there, but make sure that you can actually crank this out reasonably quickly and reliably to get the correct answer. Okay, so brush up as needed. Likewise, there's a definition of norm magnitude for that second function, that second vector. Again, this integral you have to be able to compute. It too turns out to be pi. Make sure you can do that. Lastly, looking at these two vectors, taking their inner product, using the L2 inner product, defined a couple of pages back, we find ourselves looking at this integral. And, well, gosh, there's a lot going on in that integral. Now, notice that phi is a constant here. So that phi is a constant, that phi is a constant. That means that these factors here, cosine phi and sine phi, factor out after you separate the two terms. And so really what you're left with to compute are these two integrals. So again, Calc 2, and make sure that you're able to do those. So you get this as that inner product. So putting it all together, let's see here. So that goes there. This goes there. That goes there, and altogether you just get cosine phi. All right, so the cancellation, this cancels with those. You have arc cosine of cosine phi, and so the final answer, I got ahead of myself there. The final answer is that the angle is phi. Okay, now a plausibility argument. This seems like, well, I just proved the angle is equal to the angle. That seems weird. Is that tautologous or something like that, right? What does that even mean? Keep in mind that there's two different angles that we're talking about here. The first angle that came up, this phi, that's the phase shift between two functions. So this is phase shift. Well, it's the negative of the phase shift, but directly relates to the phase shift. So what we're looking at then is two sine waves. We're looking at something like that, something like that, and phi is the phase shift between them. Right? So that's what that is. Theta is a completely different thing, at least from the point of view of how you're supposed to think about it. What is that theta? That theta says, don't look at this picture, it's not about an angle phase shift. Theta says, we want to think of these two curves as if they're vectors in an inner product space. Theta is this angle. It's the geometric angle between the two vectors in this abstract space that we can't visualize. Right? So it's really, really not obvious that the inner product space angle should necessarily be this phase shift. So it's kind of remarkable that it actually turned out to actually be that those are equal. But really fairly plausible if you think about it. I have a little bit of a geometric appeal with the phase shift. Let's kind of play through some examples. If the phase shift is 0, these are the same function. Same direction in inner product space. The angle, of course, ought to be 0. If phi is small, like I have it drawn here, well, these functions aren't the same function anymore, but they aren't that different. They kind of track each other pretty well, so they're close to each other as functions, and two vectors that are close to each other, not much angle between them. So small phi suggests you should have a small theta. Right? And then the last example of this I like to point out is, let's imagine what happens when phi is pi. Right? Here's phi being pi. If phi is equal to pi, well, then notice that this other function, this second function here, if I sort of continue it along, notice this second function is exactly the negative of the first function. Right? So when the phase shift is pi, these two functions are negatives of each other. What does it look like in hand-wavy vector space if you have two functions that are negatives of each other? If they're negatives of each other, that angle is pi. Right? So when the phase shift is pi, as expected, the inner product space angle is pi. So it's really a pretty plausible result, as it turns out. But the calculations necessary to get that actual answer. Okay. All right. One little concern that comes up. You look at this formula for angle. This angle is defined as an arc cosine. Arc cosine is a slightly worrisome function in that it's only defined if the argument is between -1 and 1. Right? So what would happen, hypothetically, if we were to end up with a situation where that was bigger than 1 or less than -1? Well, we would have a problem. You can't talk about arc cosine of 3. Right? So how do I know that this isn't nonsensical garbage? And the answer is there's a wonderful fact about inner products, and that is called the Cauchy-Schwarz inequality. And what it says is that inner products are always less than or equal to the product of the magnitudes. Right, now, y'all may remember that there was this came up in Math 212. Y'all remember the Cauchy-Schwarz inequality for the dot product? right? And it's kind of a throwaway in Math 212, because in Math 212 we have an even stronger formula, namely the dot product is magnitude times cosine. So this is sort of an immediate consequence of this more powerful result in Math 212. Neat thing about the Cauchy-Schwarz inequality, again, this applies to every inner product. Right, that business about cosine theta and all that business, that's only a result for the dot product. We use it as a definition for other inner products, but definitions aren't the same as theorems. So, nevertheless, the Cauchy-Schwarz inequality, this is a theorem, therefore sort of news for all inner products. And you might be thinking to yourself, okay, well, yeah, so what? Why is this interesting? Let's write down, I think this is just an amusing exercise, let's write down what does this Cauchy-Schwarz inequality look like for the L2 inner product. What it says for the L2 inner product is that the integral from a to b of f of x times g of x dx, absolute value, is less than or equal to the square root, right? These are norms, so square root of integral from a to b of f squared of x dx times integral from a to b of g squared of x dx. And so this is, as I've got it written here, this is, I guess you could say this is a sort of a, you could call this a theorem in Calc 2, right? This is a true fact about single variable integrals, but how in the world would you go about proving this theorem about Calc 2, right? This is a weirdly sort of inaccessible result in Calc 2, using Calc 2 tools. Right, but using the what we know about linear algebra, and linear algebra allows you to prove the Cauchy-Schwarz inequality. You can apply for any inner product. Write this down, and true. So it's inaccessible in a Calc 2 class. It's an immediate freebie in a linear algebra class. Okay. All right, so I think that's kind of neat. Okay. So I have one more example of a useful inner product I want to talk about. This goes to statistics. And if you have had a stat class before, and if you know some of these objects that we're about to talk about, such as covariance, cool. If you haven't had a stat class, don't worry about it. I'm going to tell you all you need to know for the purpose of, making this interpretation now. And then, by the way, when you do take a stat class, keep this example in mind. There's a lot of really valuable intuition to be gained from thinking about statistics from this point of view that I'm about to show you. They don't usually talk about this in an intro stat class, because in an intro stat class, the students haven't had necessarily linear algebra. So this may or may not be accessible. But this is an opportunity if you have an advantage when you take that class. Okay. A sample space is just a collection of things. That's all it is. The example that I like to use is, let's imagine a bucket full of rocks just to have, right? So we're gonna go with that as our sample space. It's just a collection of things. Random variables like x and y, these are called random variables. A random variable is just some value that you measure on each element of the sample space. So, for example, let's talk about these rocks. Maybe x is the mass of the rock. So, if you pick out a value of the sample, pick out some sample from the sample space, x, the random variable, has a value, namely what is the mass of that rock that you picked out from the sample space. Okay. All right. And you can write down any number of random variables you want. Let's talk about another one called y, which will be the volume, let's say. The volume of the rock. Okay, so you pick out that same rock. The value of the random variable x is whatever the mass is. The value of the random variable y is whatever the volume is. Okay. All right. So there is a quantity called covariance that's computed with this formula. And covariance is in a certain point of view, covariance is a kind of way of asking to what extent, when one of these random variables gets larger, to what extent can we be confident the other random variables also getting larger? And the formula for it is this right here, expected value. This just says, what would you expect? Average over all the values of the sample space. And just compute this expression. So let me draw a picture, and let's suppose let me do it like this. Okay. So we'll have our two random variables x and y, and so for each value for each point in the sample space, for each rock, I can compute for that rock what's its mass, what's its volume, and I get a corresponding point. Right? For each rock, different point. Here's a new rock, different point. Right? Now, I appeal to your intuition about rocks. Rocks that have bigger volumes tend to have bigger mass. Now, not in a perfect correspondence. Some rocks are, made out of different substances, right? So limestone's not as heavy as iron. So depending on what these rocks are made of, there's not going to be a perfect relationship here, but there is going to be some sort of a, something kind of like that. And then this one is the one that's made out of solid iron, right? It's way more massive than you would expect for its volume. But, mostly speaking, rocks with bigger mass are also rocks with bigger volume. Okay. All right. So now, for these rocks, there's going to be an average. Mu x is what is the average mass. Mu y is the average volume. Right? And let's draw that line and that line. And notice then that these things that we're averaging, all of these values in here, x minus mu x, y minus mu y, all of those values are positive over here. And all those values are positive over here. Now, they're negative over there, and they're negative over here. But look at how the rocks are related, right? Because of the fact that the rocks, the ones that are more massive, they also tend to be more volume. So bigger rocks tend to be in the upper right. Smaller rocks tend to be in the lower left. But roughly speaking, looking over all the rocks in your sample space, you're going to have, in this summation here, a lot of positive terms. And the occasional negative one, right? Look at our iron, our little odd sort of weirdo lump of iron. It's got a bigger than average mass, but a smaller than average volume. So, positive times negative. Some of these terms will be negative, but it tends to be, just because of the way mass and volume tend to correlate. Yeah, a bunch of positive terms here. So, this is what we call covariance, this expectation value of all of those products, called the covariance of the random variables. And I appeal to your intuition about rocks. We expect positive. So the idea of a positive covariance is that when one of the variables gets bigger, the other variable tends to also get bigger, usually all exceptions granted. Okay. All right. So that's the idea. Now, what are we going to do with this? First observation I'll make, it turns out that this covariance, is an inner product. I have to put an asterisk here. There is a little issue, subtle complication that I'm going to sweep under the rug for the purposes of this discussion. It's just kind of a formality. If you're curious about what that asterisk means, come talk to me after class. I'll be happy to explain. Let's not worry about it otherwise. Okay. Ignoring a minor asterisk, we have here an inner product. So, weird fact. When you're doing statistics, you're kind of doing linear algebra, as it turns out. Okay, all right, so let's put that thought aside for the moment. Okay, Here's some other things that you can define. So covariance, remember, was defined with the formula above. How a variable covaries with itself, we call variance. The square root of that, we call standard deviation. Dividing a covariance by a couple of standard deviations we call correlation. These are just objects that you'll learn about in a stat class. And again, if you haven't seen these variables in a stat class before, don't worry about it. You don't need to know much about them here. Notice, though, that standard deviation, being as it is the square root of an inner product of a vector with itself, I can interpret as a norm. And correlation, being as it is defined by this formula, is a cosine of an angle. All right, now why am I showing you all this statistics, you may ask? I'm going to show you a mystery. This used to absolutely baffle me in terms of intuition until somebody pointed out the connection to linear algebra, and then it became just immediately obvious. So I'd like for y'all to have that same experience. So for the moment, let's not think about linear algebra. Right, we'll pull out the linear algebra in a moment. Let's just think about correlation. Correlation is, you can see from the formula, it's pretty much, it's very closely related to the idea of covariance. So when we say that x and y are positively correlated, what that means is as the variable x gets bigger, then you usually, mostly, more often than not, in some sense, expect y also to get bigger. That they tend to get bigger with each other, right? More often than not. Okay. So bigger rocks tend to be heavier. Heavier rocks tend to be bigger, all exceptions granted. Okay. So let's suppose x and y are positively correlated. Let's then furthermore suppose that y and z are positively correlated. Now, let's just think it through before we get to a conclusion. If, as x tends to get bigger, y also tends to get bigger, and if, furthermore, if as y tends to get bigger, z also tends to get bigger, wouldn't you think by, like, I don't know, transitivity or something, that x getting bigger would tend to make y bigger, which would tend to make z bigger? Wouldn't you think bigger x would suggest bigger z? Wouldn't you think that x and z would have to be positively correlated? But they aren't. And again, I think this is, from the point of view that I'm presenting here, I think this is extremely mysterious. It's very counterintuitive. X and y tend to go hand in hand. Y and z tend to go hand in hand. But x and z are exactly the opposite. That can totally happen with random variables. Try to think of an example of this in the real world. It's very hard to, let's go back to rocks, right? We have the, mass of a rock. We have the volume of a rock. Maybe the third random variable could be the sort of the length, longest length between any 2 points on the rock. So mass tends to positively correlate with volume. Volume tends to positively correlate with length. Wouldn't you figure mass would positively correlate with length? There are examples to the contrary. Now, mystery. Now let me tell you why this is perfectly obvious. Right? And it comes from thinking about angles. It comes from taking a linear algebra point of view on this. Correlation can be thought of as a cosine. So a positive correlation can be thought of as as just corresponding to an acute angle, right? What a positive value of cosine means the angle is acute. So think of positive correlation as just corresponding to an acute angle inside of our inner product space. Yeah, less than 90 degrees. Okay. A negative correlation, under what circumstances is cosine theta negative? Well, if theta is obtuse. Right? So what we have here is acute plus acute adding up to obtuse. And that's not a mystery at all. That's trivial, right? Here's an acute angle. Here's an acute angle. So there's a acute angle between x and y. There's an acute angle between y and z. And no one in this room is surprised by the fact that this angle here is obtuse. Right? Easy geometry. Sometimes small plus small is large. It's no surprise at all. Okay, so that's just, so again, if you take a think about the values of the random variable, think about rocks and mass and volume point of view on this assertion about how correlation, works, this is a mysterious thought, right? But when you take the linear algebra point of view, when you think of correlation by way of this inner product construction as being able to be thought of as an angle in an inner product space, right? Then, an acute angle plus another acute angle might add up to an obtuse angle. No mystery at all. Okay, anyway, I think this is a wonderful fact to keep in mind. If you've already had a stat class, then hey, you might, think through how this might help you digest what you've already seen. If you have not had a stat class but will, I think it'd be a great idea to try to think in these terms as you're learning about those ideas. Okay. All right. Okay, so new topic. We're going to go on to section 9.2. Orthonormal bases. This idea of orthogonality. I wrote recall here. It's not really quite recall, but for dot products, this is a recall. We say that two vectors in R3 are orthogonal if their dot product is equal to 0. Keep in mind, inner products are kind of playing the role of dot products. This is our generalization of the idea of a dot product. So, in an inner product space, orthogonal means inner product is equal to 0. Whatever your inner product may be, right? If you're using the L2 inner product equals 0. Whatever. Okay, with that in mind, a couple of quick definitions. An orthogonal basis, it's exactly what you think. An orthogonal basis is a basis where the vectors are all pairwise orthogonal, right? What else would it be? Now, here is a related idea that we do have to talk about a little bit more, and that is called an orthonormal basis. An orthonormal basis means that pairwise, so the ortho part, if you will, means that pairwise these vectors are all orthogonal. But furthermore, we have the normal part. So this says that all of the vectors in this basis have been what we call normalized. Normalized means that their magnitudes are equal to 1. Okay. So this is two nice properties that vectors in a basis might have. Being orthogonal to each other turns out to be really nice. We're going to see why in a couple of minutes. Having magnitude equal to 1, also a really nice feature. Again, we're going to see why in a couple of minutes. So, a basis that has both of these nice features, it's orthogonal and it's normalized. We just say orthonormal. Yes?
Is there any geometric intuition that you have a base with a large dimension like 6, how 6 vectors could be?
Yeah, sadly, we're not built for that, right? We are built for visualizing 3 dimensions. And you can fool yourself maybe into believing that you can possibly con yourself into thinking that you can maybe visualize 4, maybe, but not 6. Nobody can do that. But it's what you're supposed to do is you're supposed to think, well, look, it's the 6-dimensional version of this, right? So perpendicular, these are perpendicular, those are perpendicular, these are perpendicular. Pairwise, they're all perpendicular. They all have length 1. But now just imagine 6 of them in a 6-dimensional space that you couldn't possibly visualize. So you kind of visualize by analogy. Yeah, right, yes.
So what kind of basis would not be orthogonal? Do they
Oh yeah, most bases. Here's one. Right, so here's three vectors. These are independent the way I got my hand oriented, right? They're all independent, but just because they're independent, these two vectors are not pointing in the same direction, but that doesn't mean that there's a right angle between them. Right? So most bases are not orthogonal. To be orthogonal, you need all of those angles to be right angles. Strictly right angles. Yeah. Yeah. So for example, here's an orthonormal basis. Right here. So I've schematically anyway drawn these three vectors here, and it's a little bit of a trick to accomplish, right? But pairwise, you can take these dot products. Those are orthogonal. Those are orthogonal. And those are orthogonal. So they're pairwise orthogonal, and all of these have magnitude 1. Thus orthonormal. Yeah. Okay. All right, so why do we care? What is so great about an orthonormal basis anyway? I'm going to give you two answers to that question. We'll see how far I get in this. Maybe it'll just be one today. But first neat feature of an orthonormal basis. By the way, quick observation. When we say orthonormal basis, both the normality and the orthogonality suggest that we're using an inner product, right? Orthogonality is defined with an inner product. Normality suggests that we can talk about the norms and that we can divide by norms to make magnitude equal to 1, which is defined with an inner product. Right? So when you're talking about an orthonormal basis, it is implicit that you're talking about for an inner product space. Right? So the first thing you should do whenever you hear words that are suggestive of, hey, there must be an inner product in play, realize that you have to then identify, wait a minute, what is the inner product that this inner product space is using? If you're in Rn, no indication to the contrary, assume the regular dot product. If you're in C, with no indication to the contrary, assume the L2 inner product. Otherwise, you need to, figure out, hopefully it's stated somewhere, you need to search and figure out where is the inner product. Okay. All right, so here's the neat fact. Orthonormal basis. Coordinates are equal to projections. Now, let me talk through what this means. Remember, coordinates, we've defined coordinates back in, when was it? We defined it in Chapter 2, but then we started doing stuff with it, in Chapter 5. Coordinates mean if you write that vector, V, as linear combination, so a C1, V1 plus ... plus Cn, Vn. The coordinates are those numbers. They're the coefficients in that linear combination. Okay, what are projections? I'm making the assertion that coordinates are equal to projections. Projections are, just think back to Math 212, it's like components. So, given a vector, V, if that's V, here, so that's V, and let's suppose that my V1 is like that. The projection, or sometimes called component, comes from dropping a perpendicular, critically perpendicular, and that distance is a projection. And recall again, now flashback to Math 212, which you're using the dot product. Projections are computed with dot products. And specifically, since these are unit vectors, dot product with unit vectors, and so you don't have to divide by the magnitude. Okay, so weird fact, coordinates are equal to projections. Now, let me explain why this is at all surprising. Here's kind of a similar picture to what I just drew. We have a vector here. And here's a basis. V1 and V2, let's say. We're just in 2 dimensions. If I want to compute the coordinates, the way I compute coordinates is I figure out how can I write V as a linear combination of V1 and V2, and that's going to come off of looking, I'm going to say, loosely speaking, looking at this parallelogram. Right? When you take linear combinations of vectors, you're making parallelograms. So that parallelogram is what's going to allow you to compute your coefficients. Well, the projections come in this totally different way. The projection comes from dropping a perpendicular. You're not making a parallelogram here, you're making a right angle. Right? So you can see how, generically, if you take some random basis off the street that's not orthonormal or anything of the sort, you wouldn't expect the coordinates computed off this parallelogram and the projections computed off this right triangle to have anything to do with each other. Okay. So the idea then is, though, that if your basis is an orthonormal basis, there's your vector, here's your orthonormal basis, you're going to compute coordinates. Oh, come on, I can draw a better line than that. You're going to compute coordinates off of the parallelogram. Oh, wow, wait a second. This is not just any parallelogram. This is an orthonormal basis. These two vectors are orthogonal. This is now a rectangle. That, therefore, is a right triangle. And so, when you're computing the projection, dropping that perpendicular, you're not surprised to get the same result. Okay, so that's just a plausibility argument. The proof is right here. It's a pretty straightforward proof. So let's suppose we already know the coordinates. So keep in mind the coordinates are coefficients in a linear combination. Suppose we know those. Okay. The way I would compute the projections one at a time is with this inner product. So I'm going to take the vector in question and then do inner products with these basis vectors. So I find myself then looking at that, but of course V is that. I invoke the linearity in inner products. Here I'm taking advantage of the fact that the inner product is linear in the left entry. Right? And now we just look at these resulting inner products. Oh, let's see here. I'm going to have to go out a notch. Most of these inner products are 0 because this is an orthogonal basis. Right? V1 and Vi, those are two different vectors in this orthogonal basis. Being an orthogonal basis, all vectors are perpendicular to each other. Inner product is 0, so that term goes away. Likewise, that inner product, again, this is an orthonormal basis. Inner product is 0. That applies to all of these terms with one exception, and that is when you're looking at Vi, inner product with Vi. And this gets to the normality. Being not just orthogonal but orthonormal, I know that the magnitude of Vi is 1, and therefore its self-inner product is 1 squared, which is 1. So that term becomes just 1. And altogether, as desired, the projections, let's see here, the projections are equal to the coordinates as required. So that's the proof. Okay. Nice little convenient proof. Now, why do we care about this? Let me show you a quick calculation. Suppose you want to write this vector as a linear combination of these 3 vectors. Now, we saw on the previous page that this trio of vectors here makes an orthonormal basis. The dot products are 0, magnitudes are all 1. That's just arithmetic that y'all can check for yourselves. So This, at a glance, looks like a chapter 1 problem. I want to write this vector as a linear combination of those vectors. You write it out, look at coordinates, make a system of equations, write a matrix, you row reduce, all this chapter 1 stuff. Which you could do, but it's kind of annoying, not least because of the fact that, look at these numbers in here, there's fractions and square roots, and right? So that's highly unappealing. Right? To proceed directly, what we're going to do is use this theorem up here. The theorem says, oh, you want to compute coordinates? You'd like to be able to write that vector as a linear combination of these other vectors? Fine. You can compute those coordinates one at a time just using projections. Projections are computed with inner products. The inner product here is the dot product, because we're in R3, and that's simple arithmetic. So therefore, we can conclude the coordinates from direct calculations of the projections. Handy. Everybody on board? Okay. All right, let's see here. I have a couple minutes left. Okay, so I want to tell you all about some other applications of this result. By the way, not all of the applications of the linear algebra that we're going to learn in this class are going to be seen in this class. With this business, there's some applications that are really interesting and very powerful, but that we just won't be getting to in Math 216. But you might see them in other places in important ways. So the first one I want to bring to your attention is Fourier Series. So some of y'all may have taken Calc 2 here at Duke. Math 122L in fall, Math 112L in the spring, whichever you may have taken. So Fourier Series is something that we throw in there. A lot of Calc 2 classes don't cover Fourier Series. Most Calc 2 classes don't cover Fourier Series. So if you haven't heard of Fourier Series, no big deal. The idea of Fourier Series is that if you have a periodic function, then you can do, in some sense of the word, a good job of approximating that function by viewing it as a combination of sines and cosines in a certain way. So it turns out that you use sine x, cosine x, sine of 2x, cosine of 2x, sine of 3x, cosine of 3x, and with these functions, etc. With these functions, a periodic function can be written as a linear combination of those simpler sine and cosine only functions. So how do you do that? Notice what the question has asked is, we would like to figure out how to write a vector, namely a function. We would like to figure out how to write a vector as a linear combination of other vectors. What we are looking for, in other words, when we're trying to do Fourier coefficients, we are looking for coordinates. We are literally looking for coordinates. Neat fact about sines and cosines, as enumerated a minute ago, they're all orthogonal. And if you go through a normalization process, figure out what their magnitudes are, divide, etc., you can make from sines and cosines, you can make an orthonormal basis. And so the way that you find these coordinates, the way that you figure out how to write some arbitrary periodic function as a linear combination of sines and cosines is by computing the projections, namely by computing some inner products. Don't forget this is using the L2 inner product, so by computing some integrals, you can compute your Fourier coefficients. So if you had Calc 2, then do me a favor, flip back and find your notes and look for the formulas for the Fourier coefficients, which will find that they're integrals. Right? Those are, in fact, L2 inner products that come from using exactly this theorem. One last little quick example. I think I've got 52 seconds. Okay. Here's a related idea, closely related idea. Image compression. So this is a very modern idea, right? The Fourier never thought about this. Okay, but how does image compression work? It's a very simple idea, really. Image compression is the idea of taking a complicated image, like a picture of me here, right? That's a complicated image, and viewing it as a linear combination of simpler images. That's what it is. All right? So, same story. We're trying to figure out how to write one image in an inner product vector in an inner product space as a linear combination of simpler images, and we want to know what are these coordinates? What are the details of how to do that? Well, you compute those coordinates with projections, which are computed as integrals in the appropriate L2 inner product. So, image compression, very powerful modern idea, is ultimately using linear algebra and inner products for your consideration. Okay, see y'all later. Have a good weekend.